Okay. Oops. So hi everyone. So this is Open-R1, a fully open reproduction of DeepSeek. I've already been introduced, but just like very shortly, I work in the science team at Hugging Face, mostly on pre-training, and more recently also on Open-R1, where I work mostly on data and code reasoning, and this is where you can find me. Okay. So the structure of this talk has three small sections, two more introductory ones about OpenAI's O1 and DeepSeek-R1, obviously, and then I'll talk about actually Open-R1, which is the title of the talk. So for OpenAI's O1, this was, as you probably know, this was the first reasoning model that came out. This was September 2024. This is a tweet by Noam Brown from OpenAI. And you can see like in this plot, they posted these results that are just much better than GPT-4o on a variety of specific, very specific problems. So these are reasoning problems, which are like this harder, more challenging kind of problems, mostly math, coding, and so on. And it just like completely beats previous SOTA models out of the water. And you can see it in these plots. So this was really the first reasoning model that came out. This is September 2024. And in their blog post, they introduced this kind of new concept called scaling test time compute. So we've all kind of heard for a while that you can just make bigger models, give them more data, and this improves your performance on a variety of tasks. So this is the left one. So train time compute scaling, you just train for longer, bigger models, more data, you get better models, right? But this is kind of a new idea they introduced, that you can actually the time the model takes in terms of compute and also time, obviously, to give you an answer is kind of correlated as well with its performance. So if the model takes longer to give you an answer, this answer can be better, okay? So this is kind of a new idea that wasn't around before. But beyond this thing, we didn't know much about OpenAI's O1. This is pretty much all they kind of said. This is from their blog post. Our large-scale reinforcement learning algorithm teaches the model how to think productively using its chain of thought in a highly data-efficient training process. So it's not much, but there are kind of two things here that are quite important. So the first one is reinforcement learning. This obviously tells us the model is kind of learning by itself in some way, like some sort of searching and exploration approach of different answers, and then going from there. And then this other idea of chain of thought, which is something that has been around for a while. If you're not too familiar, this is a sort of thing you can prompt by saying, think step by step. You're telling the model to kind of decompose the problem in different steps before just giving the final answer. So you don't want to just, give me the answer, the model gives you something. You want the model to kind of, give an actual output where it goes through different steps, decomposes the problem, and then in this way it can kind of usually get a better answer. So these are the two kind of ideas we got from this. The model learns by itself somehow, and there's chain of thought involved. Okay. And it's really interesting, like I recently opened this, I was looking at this video from Sasha Rush. So this was shortly after O1 came out, let's say a month after, and he was kind of trying to speculate about how this works. So like we really had no idea at this point. Surprisingly, many of the assumptions he made actually seem to be correct by now, but he had like 4 main suspects for the actual reinforcement learning part, which is the big mysterious one, okay? And it's really interesting because like most of them are quite complicated. These would be things where you would be having the model prompting, like generating one step of the answer at a time, branching in some sort of like tree thing, searching around, like super complicated stuff. Very interesting. People were like going crazy. Okay, how did they actually do this? Trying to replicate it. We had not much, like what is actually going on? And this was for a while. So for quite a few months, OpenAI's O1 was really the only reasoning model. Okay, that doesn't sound good. Thank you. We really had no idea what is going on. For quite a few months, this was really the only model that was out there in the market. And then come, obviously DeepSeek-R1. So this is January 2025. So already this year, they came up with this new paper. They show us this amazing plot where you can see their model is matching or even beating OpenAI's O1. And the best of all, they actually have a paper, and like OpenAI, right? So you can actually go through this thing. You can read more or less what they did. And it's really nice because then we actually finally understood some stuff about how this actually works. How you can actually scale this reinforcement learning, have models reason and think for longer and all this stuff. So how does this actually go? So actually one interesting thing is that you could, okay, maybe it's some different approach from OpenAI. But if you look at this tweet from one of the people, the researchers at OpenAI, they pretty much confirmed, this is kind of the same thing that we've done, okay? So it's really kind of the same approach. And the way it works is much simpler than all this really branching and search things people were trying to consider. So like in a very simplified way, what happens is we take some reasoning problem, and this can be, let's say, some, a high school math problem where you need like a bunch of different steps to solve to get to the final answer. You take your model, and you have it generate, let's say, n different completions, n different possible answers, okay? You then take these answers, and this is usually like some sort of chain of thought again, so like the model kind of reasoning with itself, kind of blabbing for a while with itself, and then giving you a final answer, and you check the final answer. And if you see if it's correct. So you kind of need some way to verify. This is a very key thing from this process, is you need a verifier. So you need a way to check, given a model output, if its answer is correct for this problem, okay? So you take this thing, you take the 9 completions, 9 possible answers, you check which ones are correct, and you basically just make the correct ones more likely and the incorrect ones less likely. And this is the entire optimization step. Obviously, you have GRPO, which is group towards policy optimizations, and it's a bit more, obviously the loss function and so on is a bit more complicated than this, but this is kind of the key idea, okay? So you generate a bunch of completions, you take the ones that are correct, and you make them more likely. And obviously, the reward does not have to be completely Boolean, it doesn't have to be correct and correct, you can have some sort of partial thing to help the model speed along, but this is really the main idea, okay? So we also see this thing which is very reminiscent of this earlier plot I showed you from OpenAI. So the idea here is, this is not so that the inference, so this is as they are training, so the steps they are doing in reinforcement learning here on the x-axis, and this is the length of the model. So on average, as you are training with this reinforcement learning approach, the model starts to give you longer answers, okay? It's not like you controlling a test time for something specific, it's just like by itself, through this process, what happens is that as models try some completions that are longer, usually they are more correct. So the model just learns to give you longer answers in general. And this is what you get. Like as you keep training the model, length keeps increasing. And there's been very added research on top of this, where people are trying to, okay, maybe this is actually not so great. We don't want it to go so high. So people are like changing the reward function a bit. But this is actually really interesting and kind of goes back to this OpenAI plot. Another thing that was really kind of broke people's mind a bit is this aha moment. So as the model is reasoning with itself, so in this like part of the answer where this recomposing the problem, kind of arguing with itself for a bit, sometimes it just backtracks somehow, right? So this is not like people before would think, okay, so maybe actually we generated this, we had some other model come in, try to correct it. No, this is just a single generation. As the model is going, it just corrects itself, goes back, and it keeps doing this thing. And it sounds really cool, but sometimes you look at the trace and just model just keeps going, wait, okay. And sometimes it works well, sometimes not so much, but it's also something that they had pointed out in the paper, and it's really kind of interesting as well. Another very interesting thing. So basically, they take this very powerful model called DeepSeek-V3 that they released on December last year, and they apply this reinforcement learning process on top, and they get DeepSeek-R1. But something else they also do is distillation. So this is not very like classical distillation. It's more like you take some problems, you have the large, very powerful model give you outputs for these problems, and then you train on these outputs, or the model outputs directly, okay? So no reinforcement learning involved, it's just normal fine-tuning, but with answers that already have the reasoning traces from R1. And what they show is if you take, let's say, a less capable model, such as QN32B, because it's like a much smaller model, like a DeepSeek, like V3 is really huge, and you apply reinforcement learning directly on top, it does give you some results, but these results are nothing compared to just taking the distillation, so taking the chain of thought generated by DeepSeek-R1 and training on that directly. So this is the last model here on the line, which is this distill model, completely beats the DeepSeek-R1 0 queen. Okay, so this is really interesting because it kind of shows you two things. One thing is that, like when you're doing this thing where you're generating multiple answers, the whole point is if the model can never actually get the problem correctly, you're not actually improving because you need at least some correct options on the generations. Like we have n generations. If they're all wrong, the model is not going to optimize anything, right? You have no reward there. And the other thing is that obviously, so you need stronger base models. And the other thing that this kind of shows you, okay, so if you need stronger base models, all these talk people like to say, like pre-training is dead. We just can do all this reinforcement learning stuff on top. It's actually not true, which is great news for me because I work mostly on pre-training. But you actually need you need to keep working on pre-training. You need to make better, stronger base models because these effects, like a stronger base model, really multiplies it's the performance effect of the post-training and reinforcement learning steps. So in conclusion, better base models, result in better reinforcement learning. And actually, if you have a less capable model, you're better off by actually distilling from the better one. Which leads us to Open-R1. And you might be thinking, okay, so why open? Isn't DeepSeek-R1 already open? I can download the weights. You can, but you don't know, like you don't have the training code. You have no analysis of like how this actually scales, what are possible trade-offs. You don't have any verifiers, and most of all, you don't have any data at all. Okay, so you cannot actually, if you want, and you have the resources, you cannot just go and git clone or load data sets from Hugging Face, everything you need, and just make your own R1. You can't. We don't have this stuff. Okay, and while it's really nice that they have a paper and that really has pushed research in this area forward, there's still much to do in terms of like actually open science and open things that can be reproduced. This is the idea behind our project. Okay, so we want to kind of go through the entire thing, guided by their paper and by the results, and just rebuild the entire stack. Okay, so we kind of had 3 stages planned for this. So the first one is still related to distillation. So the idea is, let's say, you know, we want to reproduce these distilled models. So we take the actual DeepSeek-R1 model. So this very powerful model that released with all the reinforcement learning on top. We take some problems, some reasoning problems. We have the model generate outputs, and then we just do supervised fine-tuning on top. And the idea is that we want to get models comparable to the ones they released, the distilled models they released, okay? And the whole community, so it's not just that, it's like a thing that is going on in the entire research community, has been allocating a lot of GPUs to this effort. So this is like a week or 2 after the release of R1. There were already all these data sets out there, some from us, some from other people, and these are basically people taking reasoning problems and just having, you know, DeepSeek-R1 on a lot of GPUs and just generating a lot of outputs to then be able to do the fine-tuning and get distilled models. So people have focused mostly on math. We ourselves, we had like 500 GPUs going for a few weeks working on this. And you know, maybe you're wondering, okay, so but what is actually reasoning problem? So this is a bit of an extreme case. This is like a very hard class of problems, which are problems for the mathematical Olympiads. But just to give you an idea, so these are things from like proofs, things where you need to find all numbers that fill some sort of condition. And these things are very hard. So if you look on the right, you have a solution to the first problem. This involves multiple steps. They're quite complex, and it's not something the models can usually just zero shot and just give you the correct answer. So this is where all this kind of step-by-step approach really shines. And this is the kind of things we're contending with. So obviously there are simpler problems. This is like more of an extreme case, but these are the sort of things you need for math. So one other thing that is kind of important, we've spoken about verifiers. And at this point, you're not doing reinforcement learning, but one thing that is interesting is, okay, let's say we have all these outputs coming from DeepSeek-R1. Is there a difference? Like, because some of them might be wrong, right? We don't know. And actually, one interesting assumption when you do, even when you do verification in reinforcement learning, is that we assume, okay, if the answer is correct, if the problem is hard enough, then probably the reasoning kind of makes sense. Like, but we actually don't know, like, because we're not looking at the reasoning traces. But we're just looking at the final answer. But even looking at the final answer is hard. Why? Let's say we have a math problem, and even if it's a simple kind of direct solution kind of thing, where you give a final number. Let's say the model gives you 0.5, and the gold answer you are comparing with is 1/2. I mean, they're the same thing, right? But you cannot just do equals on this thing. It's more complex than that. And you can even go even more complex. You can have things with sets and unions and whatever. You can have sometimes percentage and decimals. You can have units just by, you know, because someone had units. You can have 0.333 instead of 1/3, all these sort of things. So one of the first things we worked on was a library, which you can use, and it's very simple to use. You just have you parse your gold answer, you parse your answer, and you compare them. It's just called Math Verify. And one thing we did, so we took our generations from DeepSeek-R1 for math problems, and we verified them. So we checked which ones are correct. And what we did is we took these data sets, and we fine-tuned some models. And actually, you know, we kind of managed to reach the performance of one of the distilled DeepSeek models. So this is the DeepSeek Distill Queen 7B. This is the one we made. This is one someone else in the community made. And you can see, like, on math benchmarks, okay, and AIM25 is slightly behind it. Like, on the rest, you know, pretty much match this performance. So, you know, like, this idea of the distillation actually works. We can actually reproduce it. We can actually take DeepSeek-R1, generate some math problems, and take some model which was much weaker before, and just fine-tune it and have it become a reasoning model. Okay. Something else people often talk about is code. So that's another classical example. So what is like a code reasoning problem, right? It's not so much change the color of my background. It's more complex stuff. So usually, so this is Code Forces, for example, is a website which you can think of as LeetCode for fun, okay? because some people do lead code for fun. And actually, the way this works is you have a problem description. You have like some classical problem, kind of resembling math problems from school. And then you have input description, output description, and some examples. So the idea you test this thing is you make some code, and then you test it on a bunch of test cases. So each test case has an input and an expected output. So the idea is that if your program, and this is how they are tested on these competitive program websites, as you can see here, you submit some codes and it is tested on a bunch of test cases. If it successfully solves all these test cases, then it is correct. One important caveat though is that it needs to solve them within the time and memory constraints. Okay, because the whole point here is that you need to have something algorithmically optimized. You cannot just do a brute force solution, because that is not the idea of the point of this thing. That is, have something quite optimized that can solve this problem within the time constraints. So you can imagine that these sort of problems are quite interesting, but there's not that many of them out there. So what we did is we actually took the ones from that website I was showing you, so from Code Forces. We parsed all the descriptions, we took a vision model to convert the LaTeX, everything. And again, we just did the same thing. We took DeepSeek-R1. We loaded up a bunch of GPUs, and we just generated solutions with this model for these problems. Okay. And then what we did is, so this is Code Forces chain of thoughts dataset. That's the original problem description dataset. We again fine-tune a model with this. But for coding and like math, there's not so much benchmarks for these more reasoning kind of things. So you have more classical software engineering problems like Live Code Bench and all this stuff, but not so much for that. So we actually made a new benchmark. We call it, so this is based on the International Olympiad in Informatics. A very nice thing about this competition is that all the test cases are public. So they give you the full test cases that were used on the live competition. Okay, so what this means is that we can actually be sure that if the solution generated by a model passes all the test cases, then it is actually correct. And I'll get to that, why the availability of test cases is important in a bit. But we took this model that we fine-tuned, we called it Olympic Coder. It actually performs really well if you kind of test it within model conditions, which is you have a limited number of submissions. You might be wondering why qual 3.7 is down there. If you actually look at some of the generations, it's really very interesting because it does not really want to follow instructions sometimes. Like you say, we have some boilerplate codes, you should fill this in for a real thing, or you should, which is something quite frustrating about quad 3.7, but kind of explains this idea. And like this is again, like the distillation claims kind of check out. You can actually achieve the same performance or close to the same performance as their big model, which is like distillation. So this is more or less what step one was about. And okay, we actually want to do some reinforcement learning as a next step. So we want to take some base model, we want to do GRPO with verifiable rewards, and obtain this first model, which is the one that DeepSeek also got, which is they got DeepSeek-R1 0. So after a pure round of reinforcement learning, you get this model. This is not the final model they released, okay, because the one they released went through different rounds of fine-tuning and reinforcement learning, one after the other. But this is kind of what we want to do for step two. And I mean, like you need GRPO, then you need the algorithm, or you need some other equivalent. I mean, it's not like GRPO is really the breakthrough here. It's been around for a few months, actually, since last year. But it's part of TRL, so this is Transformers Reinforcement Learning. It's a library by Hugging Face for post-training, and it's actually really easy to use. Okay, so like you take a data set, you code up a reward function, so this is something that takes a model completion and gives you a result, and you just make a trainer and you call it on a different specific model you want to GRPO. So like in this case, we have Quen to 0.5b instruct. Okay, and this has been optimized for months now since it came out. People have been working on this, making it more optimized, more scalable. It's really easy now to do this sort of thing. Okay, so this brings me to, okay, so we're actually doing reinforcement learning. I've already touched a bit on why verifiers are important. And I want to do it for code specifically, because for math, you take the final result to check if it's correct. For code, as I told you, you need to run through a bunch of test cases. So what happens if your test cases are not good enough, or if you don't have enough test cases? So actually, if you look at what the platform gives you on the left, so this is if you open a submission on Code Forces, for longer test cases, for very normal reasons, they don't want to crash your browser window, they just truncate the test cases. So they give you like the first 400 characters. And what happens, like when you take a data set that is meant to be verifiable problems, so let's say DeepMind code contests, and you start to look, okay, so on the left you have the examples, these are in the problem statement, on the right are the rest of the test cases they test on, And sometimes you have like 1 or 2 test cases. Sometimes the only test cases you have are literally just the examples. What happens if you are doing reinforcement learning where the only way to verify a problem is with the test cases already shown to the model in the examples? The model will literally hard code these examples. If you look at the code the model generates and just checks if the input is the first case, print the correct solution. If it's the second case, print that solution, and there's no other test cases to check. You'll be saying, this solution is correct. You're optimizing the model to learn to do this thing, and it's just not what you want. You don't want the model to just give you back the examples you gave to it, right? And what I'd say, as I told you, it needs to pass the time and memory constraints. So what happens if you just have very short test cases that really don't push the limits of the input? You'll be optimizing again with like incorrect solutions, and you'll be thinking they're correct. And you have an example. So let's say we took a few problems from these data sets. We had Open-R1 generate solutions. We actually ran them through the tests we had on this data set. It passed all the tests, but if you actually submit them to the platform, they're all wrong. Like not a single one of them was correct. These are, more challenging problems. So obviously for some problems the output was correct. But there are many problems where you would think they are correct if you take the verifiable test cases in these data sets, but they are not actually correct. And to make it even worse, so there's this Queen paper called Code-Elo where they try to evaluate models on code forces, and actually they conclude the easiest thing is really to just submit the solutions to the website because it's very hard to verify. Some problems even have multiple correct solutions. If you look here, if there are multiple solutions, print any of them. So the idea here is that when you evaluate these problems, you need a special checker. So it's actually like one of the things we've been working on. So we took these around 30% of problems that require a special checker, and we actually had a pipeline. So we take Open-R1 and we ask it to generate a checker that given a correct solution and some generated solution checks if they are correct. And then we evaluated some of these with actual correct solutions from the problem. So if these are considered correct by our checker, then we think it's a good checker. And for the test cases, you can apply a similar idea. So let's say you take some correct solutions and some quite good incorrect solutions because they pass most of the test cases, but not all. And you generate some test cases. You see if they are valid by the fact that the correct solutions can solve them and agree on the result. And then you see if they are challenging enough to weed out this incorrect solution. So this is kind of things that you should need to do. Like you cannot just take some half-baked verifier, which kind of sounds correct, and run your stuff with this, because then you're verifying things that are wrong. To give you some more examples, so here what this actually looks like in practice. So this is a training run of a relatively small model, so 7B, with 2 reward functions. So one is just to have the model print the correct tags. So like we have a function that checks, it's literally a regex, you have it here. There's a think, a close think, answer, a block of code in the language we want, and a close answer thing. And actually this is very easy for the model to run. You can see that after a few steps, it just has a reward of 1. It just starts obeying the format perfectly. But if you take this thing, which is actually solving fully verifiable problems, it's much noisier. Like it still goes up, plateaus a bit by the end, but it's much noisier. So like even the way you create these reward functions is very interesting because again, if you had a simple, fully correct or incorrect, it might bump around a bit more. So in this case, actually what we do is if you solve some of the test cases, you have some reward. If you solve the full problem, you have much higher reward. And so there's all these kind of things that you need to consider when you're doing this sort of work, which is how you define your reward functions and how you weigh them and all this sort of approach. To finish off, this is kind of a next step we're not working on right now, which is kind of putting everything together. Okay, so this is you're taking some of the reinforcement learning steps, some of the fine-tuning distillation steps, doing this thing in a bunch of iterations, and actually obtaining a model comparable to DeepSeek-R1, a final Open-R1, if you will. And we're not quite there yet. But this is more or less the entire pipeline. And that's my talk, so you can actually follow the project along on this Hugging Face organization or on GitHub. And now I think we can have some questions.